Hey, we're back again, reading quiz number 9. Don't you just wish that we had some sort of a way to find derivatives without having to do all those difference quotients and all that stuff? All right, well, let's try it out. Let's see what we got. Rules for derivatives. So let's start with some basics, which some of them hopefully kind of figured them out as we've gone along. The first one's the constant rule. Basically, it says that if we take the derivative of a constant, let's say y is equal to 5, the derivative is equal to 0. I hope this makes sense as we start to connect derivatives with slope. The line y is equal to 5 is a horizontal line with a slope of 0, so therefore the derivative should be 0. Makes sense. Another rule that we'll encounter a whole lot over the course of the rest of the AP calculus is the power rule. And basically that says if n is a real number, the derivative of x to the n is n times x to the n minus 1. So that's if you have a numerical exponent. Say, for example, y equals x to the 7th. The derivative of y equals x to the 7th would be 7x to the 6th. The other two rules we will use in conjunction with the power rule and with some of the other rules we'll learn. Those rules are the sum and difference rule and the constant multiplying rule. The sum and difference rule basically says that the derivative of the sum of two functions is the sum of the derivatives, and then the same with subtracting two functions. The constant multiplying rule will say that if we are multiplying a function by a constant, that derivative of the constant times the function will be the constant times the derivative. So let's take a look at the power rule, which we'll be using a lot. And we'll start with a very simple example. Let's say we wanted to find the derivative of y is equal to 5x plus 7. We can take two different approaches to this. The first one is to realize that this is just a linear function. And as I said, we're going to connect slope with derivative. And so the slope of this linear function is 5. Therefore, the derivative of y equals 5x plus 7 would be 5. Well, the second approach is to use the power rule, which we just talked about, and which we'll prove at some point in the near future. So the way we would use it is we would say, well, y is equal to 5x to the first plus 7. Using the power rule would say that we need to bring the exponent down, and that would make that 5 times x to the 0. And we know that 5 times x to the 0 is the same as 5 times 1. We're also in this using the sum and difference rule by taking the derivative of each part separately. One of the things that we should note is the derivative of 7 by our constant rule is equal to 0. Okay. Well, this example number 3, looks a little more challenging. I wonder if we have y is equal to 1 over x plus 2 over x squared. In order to use the power rule, we need to make sure that we simplify first. In this case, we notice that we do have numerical exponents, so we could rewrite our function as y equals x to the negative first plus 2x to the negative 2. You also need to be very careful in how you simplify. Notice that the 2 is in our numerator. Make sure that you take care not to put it in our denominator. Through our power rule, we will bring down the exponent. So the first part, the derivative of the x to the negative first, would be negative x to the negative 2. We're subtracting 1 from negative 1 to get our new power of negative 2. In addition, when we take the derivative of 2 times x to the negative 2, we get negative 4 by bringing that negative 2 exponent down. And we need to subtract 1 from our old exponent of negative 2. That'll give us negative 3. And notice that throughout we are also using the addition rule for derivatives. Yes, I will ask you to simplify this. When we do our work, we will find that we can simplify this derivative as negative 1 over x squared minus 4 over x cubed. And we will talk about that in class. Here's another example using the power rule. Y equals negative x squared over 4 plus 3 times the square root of x. Well, a couple of potential pitfalls here. The first is to realize that we've got a 4 in our denominator of the x squared term. So when we rewrite, we're going to need to rewrite that as negative 1/4 x squared. Move that fraction out. In addition, 3 times the square root of x is written as 3 times x to the 1/2. All right, remember that if you have a square root, that becomes something to the 1/2 power. And now we can just apply our power rule. All right, in doing so, we get negative 1/2 times x, because our exponent 2 will need to be subtracted by 1 to get our new power. Same thing with 3x to the 1/2. We get 3 times 1/2 is our new coefficient. And then our new power will be 1/2 minus 1, which is x to the negative 1/2. A quick note about what are called higher derivatives, or derivatives of higher order. If the derivative of a function f is also differentiable, meaning we can find the derivative of the derivative, we call that the second derivative. And that's usually denoted with an f with 2 marks there. All right, they look like apostrophes, but technically they're actually a different symbol. All right. Furthermore, we could have a third derivative, which would be the derivative of the derivative of the derivative. We go so on with the fourth and the fifth derivative. So if we're using our f prime notation, right, that would mean that our first derivative would be f prime of x, second derivative would be f double prime of x, third derivative f triple prime. After a while, we get tired of writing those little tick marks, so we end up just writing the fourth derivative with a little 4 and the fifth derivative, and so on. If we're using the Leibniz notation, if you'll remember, we originally wrote the derivative as dy dx. The second derivative has a little bit different of a notation. The 2 in the numerator goes in between the d and the y, and the 2 for the denominator goes after the x. We're indicating that we're taking the derivative twice, that's the d operator, the derivative, with respect to x twice. So the x gets the 2 in the denominator, and the derivative part gets the 2 in the numerator. And then same thing for all the future derivatives. Another rule which will be useful is if we're multiplying two different functions. Let's say those two functions are both differentiable. We'll call them f and g. All right. In order to find the derivative of f times g, we have a formula which we will prove at some point when we do our proofs. And that derivative would be f of x times g prime of x plus g of x times f prime of x. Looks a little complicated. It's not quite as simple as you might think. So here's an example. Find the derivative of y equals parentheses x squared plus 1 times the quantity x cubed plus 3x. So you notice that we are multiplying two functions together. You could go through in this particular example and FOIL, and then find the derivative of each component of each term using the power rule. However, I'm going to show you how to use this, how to find the derivative using the product rule. All right, so let's use a little helper here, a little diagram. What we're going to do is we're going to identify our two functions that compose our product. Those two functions are x squared plus 1 and x cubed plus 3x. Below those two functions, we're going to put the derivatives. The derivative of x squared plus 1 is just 2x. Don't forget about the constant rule. The derivative of the constant 1 is just 0. And the derivative of x cubed plus 3x is 3x squared plus 3. And notice I put a little x in there. And the x, if you'll remember from way back in elementary school, denotes multiplication. In this case, it's actually just a device to help us realize how we're going to use the power rule. We will multiply top left times bottom right, and add that to what we get when we multiply bottom left times top right. So here we get x squared plus 1 times 3x squared plus 3 plus 2x times x cubed plus 3x. And yes, I will ask you to simplify. When you do so and gather terms, like terms together, you get 5x to the fourth plus 12x squared plus 3. Another situation you might have is if you have a table of values and a function's given, let's say k of x is equal to 3 times f of x times g of x. And the question would ask you to find k prime of negative 2. In this case, please, before you plug anything in, find the derivative of the function that's given. In this case, we need to find the derivative of k of x, which is composed of a product, 3 times f of x times g of x. It really doesn't matter where you associate the 3. In this case, I'm just going to put it with the f of x to make life easier. And using our constant rule, we know the derivative of 3f of x would be 3 times f prime of x, and the derivative of g of x is g prime of x. By the product rule, that would give us a derivative of 3f of x times g prime of x plus 3f prime of x times g of x. And now, once we've found the derivative, remember, we don't want to take the derivatives of constants. So let's find the derivative first, which we did, and now plug in our value x is equal to negative 2. We can go to our chart, find out what f of negative 2 is. That would be 7. What g prime of negative 2 is, that's 6. And so on. We plug in our values, simplify, and get 72. A final rule that we'll be using is if we've got a quotient, all right, some sort of a rational function typically. And what the quotient rule gives us is a way to find the derivative of a function that's in the form f of x over g of x. And that gives us a formula that looks even more complicated than our product rule formula. The derivative of f of x over g of x would be g of x times f prime of x minus f of x times g prime of x over g of x squared. Notice the numerator is slightly different from the product rule because we have a minus in between the two. It looks complicated, but we've got a way to remember this. So I'll lead you through this way to remember through an example. Let's say you have y equals 2x squared minus 1 over x cubed plus x. Our way to remember the quotient rule is a little mnemonic, which goes like this. We say low d high minus high d low over low low. Low represents the low function. In this case, it's g of x. D high represents the derivative of the high function. So we get low d high minus high d low over low low. You say it a few times, it's pretty easy to remember. So in this case, we apply low d high minus high d low over low low. Low is x cubed plus x. D high is 4x. High is 2x squared minus 1. D low is 3x squared plus 1. And low low, which is low squared, is x cubed plus x all squared. Yes, I will ask you to simplify the numerator. When you do that, you get negative 2x to the fourth plus 5x squared plus 1 over x cubed plus x squared. Let's try this again with a chart. Let's say we knew our function p of x was equal to g of x over f of x plus 1, and we want to find p prime of 3. Just like with the product rule example, you want to make sure you take the derivative before you start plugging in things. When we do that, we get low, which is f of x plus 1, d high, which is g prime, minus high, g of x, times d low, which is f prime of x, over low squared, which is f of x plus 1 squared. Now when we plug in 3 in for x, and we go to our chart, we take a look, we find f of 3, which is 1, plug it in, g prime of 3, which is 4. At this point, it's just a bunch of table reading and plugging in values, and hopefully simplifying your algebra and your numeric values correctly. We get down to the point where we have negative 11 over 2.